Welcome to the series in Mineralogy. And before tackling the subject, it will be well apt to understand first what mineralogy is. Well, put simply, mineralogy is the scientific study of minerals, but more specifically, mineralogy involves the study of their internal structures and compositions, their physical and chemical properties, their classification, their modes of formation, and the occurrences and associations of those minerals. This is mineralogy, but to be able to start studying it, we must also understand what it is that we are studying. It is extraordinarily difficult to provide a sufficiently precise yet concise definition of mineral that would satisfy everyone. Historically, people used to call any stone a mineral if metal could be produced from it. And in our current everyday language, mineral can be any material which is not made by plants and animals. But that would make mineralogy everything except biology. This definition cannot serve our purpose. So now, let us proceed towards the definition which most, if not all, mineralogists agree, which is that a mineral is a naturally occurring, homogeneous, solid substance of generally inorganic origin with usually a well-defined crystalline structure and a chemical composition that lies between well-defined limits. This definition is necessarily long to include all the materials a mineralogist wants to study, and even then, which we'll see further, this definition has small loopholes. Let's understand this definition word by word. So, a mineral is a naturally occurring substance, but this would rule out synthetic gems like sapphire, ruby, and emerald from being a mineral. But these are still minerals because there is a natural counterpart here, whereas plastics are not minerals because plastics cannot be formed under natural conditions. Minerals must be homogeneous at the limit of electron microscopy, that is, the nanometer range. Due to this part, plagioclase felspar, which appears to be homogeneous to the naked eye, cannot be a mineral because it is composed of minerals albite and anorthite, which are the end members of the plagioclase felspar series. Also, minerals must be solid, but water and liquid mercury are sometimes also considered minerals because, well, ice and solid mercury were a mineral before. A mineral must also be of inorganic origin, but this would exclude calcite in limestone and calcium phosphate in phosphate depositions because these minerals are the remains of plants and shells and bones respectively. Also, coal is a complex mixture of materials, some of which are truly minerals and others are clearly of organic origin. And strictly, this makes coal not a mineral because it is neither homogeneous nor inorganic. Minerals also have to be crystalline, although the degree of crystallinity may be sometimes very small. But minerals like opal, a solid silica gel, do not have any long range order and absorb a wide variety of elements as they grow in aqueous environments. Instead of disregarding these materials as non-minerals, they are called amorphous minerals. Finally, minerals must have a fixed chemical composition but within well-defined limits. Diamond is C, galena is PbS, and the one shown here quartz is SiO2. But these compositions are only roughly constant as diamond contains variable amounts of nitrogen, galena has sometimes traces of silver, and quartz commonly contains trace amounts of titanium and iron. This is why the chemical composition of minerals cannot be absolutely fixed but fixed within limits. This completes the definition of a mineral. Some of the minerals are sometimes described as metameric because they were originally formed as well-ordered crystalline solids, but eventually their crystal structure got destroyed to various degrees due to radiation from radioactive elements present in the original structure. Zircon or ZrSiO4 commonly contains both uranium and thorium, and consequently, as shown in the upper central part of the image, the mineral's crystal structure has been destroyed. There are also substances called mineraloids that have some of the properties of minerals but are not regarded as valid minerals, usually because they have not been formed exclusively from geological processes. Hence, pearl and organic crystals in plants are mineraloids. However, some biogenic substances were subsequently found to be formed by geological processes as well, such as unary calculi, bevelite, and bedellite. These then qualified as mineral species. Let us also give time to consider what is not a mineral. Rocks are not a mineral, rather, they are naturally occurring coherent aggregates of mineral grains, like granite, shown above, which consists of minerals like the flesh-colored felspar, white-colored quartz, and black-colored hornblende. Also, some rock types may be aggregates of the grains of a single mineral, like diorite, which is composed entirely of all minerals. Such rocks are called monomineralic rocks. Quartzite made of quartz and marble made of calcite are also monomineralic rocks. Minerals are also not mineral deposits, which are unusually rich, naturally occurring concentrations of a particular mineral or element. Although the proportion of mineral in a mineral deposit should be, by definition, higher than the average crustal composition, the mineral may nevertheless account for a very small mass in the deposit. For example, any potentially valuable diamond deposit, such as Kimberley in South Africa shown here, just needs to have one part of diamond in a million part of rocks. Further, some of the mineral deposits are called ores when it is profitable to extract the mineral from the mineral deposit using the existing technological methods. There are tin ores, copper ores, gold ores, and iron ores like the one shown here, but many mineral deposits are not ores at present, but they may be in the future as technology progresses. As shown in the right side figure, study of minerals is central to many branches of geology, so much so that now it is being referred to as mineral science. The graph shows how much mineralogy has impacted other sub-branches of geology. Coming over to mineral names, minerals have been given names since before the dawn of history, but today the introduction of new mineral names is strictly controlled. Publication of new names require prior approval by the Commission on New Minerals Nomenclature and Classification of the International Mineralogical Association. In addition to valid mineral names, other names are also used for particular variety of minerals, especially those with descriptive coloring. For example, deeply colored varieties of corundum have been given varietal names like ruby and sapphire. Such names have no validity as species names and their use is not controlled by CNMNC. So let's end this introduction with some speculations about the future. Over the past 200 years, we have identified more than 4,500 minerals. Major inventions in the timeline of mineralogy, from the polarizing microscope and crystal diffraction to the electron microscope, has sparked renewed interest in mineral discovery in their times. But will such rapid expansion continue? The answer is yes. In fact, in 2014 only, we discovered bismuth, the most abundant mineral in Earth, making 93% of the lower mantle. And with ever increasing advancement in space technology, the possibility of applications of mineralogical concepts is bigger than it has ever been. Thank you.